Feynman said near the end of his life that there was one problem he could not crack, not one he hadn't tried, not one he found uninteresting. One he had worked on, returned to, approached from multiple directions, and still could not solve. He said it in a lecture at Caltech in 1964, and he repeated it in interviews until his death in 1988. The problem is not exotic. It is not buried in the outer reaches of cosmology or the speculative territory of quantum gravity. It is visible in every river, every cloud, every column of smoke rising from a candle flame. It is the problem of turbulence. Why fluid, when pushed hard enough, becomes chaotic in a way that no equation we have can fully predict. We have the equation, we have had it since 1822. The equation is exact, and we cannot solve it. That is the situation. Not that the physics is unknown, not that the mechanism is mysterious. The mechanism is written down in precise mathematical notation, and it has been for 200 years. The situation is that the equation is correct, complete, and practically unsolvable, and the gap between having the equation and understanding the equation is so large that it constitutes one of the 7 Millennium Prize problems identified by the Clay Mathematics Institute in the year 2000, each carrying a prize of $1 million. 6 of those problems are in pure mathematics. 1 is in physics. It is the problem Feynman said he could not crack. But turbulence is not the only layer of this story. It is the most visible layer. Beneath it is a second problem, harder and stranger, that Feynman spent more time on, and that remains, as of today, completely unsolved. It is the problem of confinement. Why quarks, the fundamental constituents of protons and neutrons, cannot be separated ever, under any circumstance, no matter how much energy you apply. Every other force in nature weakens with distance. Gravity follows an inverse square law. Electromagnetism follows an inverse square law. The strong nuclear force does the opposite. The farther you try to pull a quark away from its companions, the harder the force pulls back, not weakening, but strengthening, like a rubber band that never snaps. And no one has derived this from first principles, not Feynman. Not anyone since. These 2 problems, the churning of a river and the imprisonment of a particle inside a nucleus, look nothing alike on the surface. One is classical, one is quantum, one is visible to the naked eye. One requires a particle accelerator to even confirm, but they share a single underlying disease. They are both problems of strong coupling, situations where the coupling constant, the number that measures how hard the forces are pushing, is so large that the mathematical tools we have stop working, not approximately stop working, completely. The perturbative methods that Feynman himself invented, the diagrams, the path integrals, the renormalization procedure that made QED the most precise theory in the history of science, all of them assume the coupling is small. When the coupling is small, you can organize the calculation into a series where the first term dominates, and each subsequent term is a small correction. When the coupling is large, every term in the series is as large as every other term, and there are infinitely many terms. The series is meaningless. The calculation collapses. This is the structure of what Feynman left behind. 2 phenomena. 1, underlying disease. No cure. And before going into the details of either problem, it is worth saying clearly what kind of problem this is, because it is genuinely a new kind, one that did not exist in physics before the 20th century. For Newton, Maxwell, Einstein, Schrödinger, the hard work was finding the equation. Once the equation was written down, its consequences could be extracted. With strong coupling, the equation is found, the equation is confirmed, and the consequences, in the regimes that matter most, cannot be pulled out. The equation sits on the page exact and complete and refuses to give up its answers by any analytical method known to mathematics. Start with turbulence. It is the one you can see. Water flowing slowly in a stream is laminar. The molecules move in parallel layers, each sliding past the next with minimal mixing. If you inject a thin thread of dye into laminar flow, the thread stays coherent. It moves downstream in a clean line without dispersing. This is the regime where the Navier-Stokes equations are not just solvable, but easy. Every quantity behaves predictably. The velocity at any point in the fluid at any time can be calculated from the equations with as much precision as you want. Osborne Reynolds, working at the University of Manchester in 1883, was the first to quantify the transition from this orderly regime to chaos. He defined a dimensionless number, now called the Reynolds number, abbreviated Re, as the ratio of inertial forces to viscous forces in the fluid. Re equals the fluid density times the velocity times the characteristic length, divided by the dynamic viscosity. At low Reynolds numbers, Below roughly 2500 for flow through a pipe, the flow is laminar. Above 4000, the flow is fully turbulent. Between those values is a transition zone where neither laminar nor turbulent behavior dominates, a no-man's land that Reynolds himself spent years trying to understand, and that still contains unresolved physics today. What Reynolds found when he injected dye into a pipe at different flow rates was not a smooth transition. At low velocities, the dye thread was clean. As he increased the velocity, at a certain point the thread broke. Not gradually, suddenly. The dye dispersed instantly into a chaotic mixing pattern that filled the pipe cross-section within a few pipe diameters. He published these results in the Philosophical Transactions of the Royal Society in 1883, and the paper remains one of the most cited in fluid mechanics. What Reynolds could not explain, and what no one has explained since, is the precise mechanism of that transition. Why does the dye thread hold, and then break? The Navier-Stokes equations describe both regimes. They describe the transition, but solving them analytically for a turbulent flow, finding a closed-form expression for the velocity field as a function of position and time, is not something anyone has managed to do for the general case. The equations are nonlinear partial differential equations. The nonlinearity is the problem. It couples every scale of motion to every other scale, from the large energy-injecting eddies at the scale of the pipe diameter, all the way down to the tiny Kolmogorov microscale, where viscosity finally dissipates energy as heat. In a turbulent pipe flow with a Reynolds number of 100,000, the ratio between the largest eddy scale and the smallest dissipation scale is approximately 100,000 to the 3/4 power, roughly 5,600 to 1. Every one of those scales is coupled to every other. The calculation is not just hard, it is not reducible. The Navier-Stokes equations themselves were formulated between 1822 and 1845, the work of Claude-Louis Navier in Paris and George Gabriel Stokes in Cambridge, each working from different physical assumptions and arriving at the same equation. The equation expresses Newton's second law, force equals mass times acceleration, applied to a fluid element. It says that the rate of change of momentum of a fluid element equals the sum of the pressure gradient force, the viscous force, and any external forces. In vector form, the momentum equation reads, the partial derivative of velocity with respect to time, plus the velocity dotted with its own gradient, equals -1 over density, times the gradient of pressure, plus kinematic viscosity, times the Laplacian of velocity, plus external force per unit mass. The term that causes all the trouble is the second term on the left side, velocity dotted with its own gradient. This is the nonlinear term. It represents the fact that the fluid is carrying itself, that the velocity field advects itself through space. It is a quadratic nonlinearity, and it is what makes the equations intractable in the turbulent regime. Remove that term and the equations are linear, easily solvable by standard methods. Keep it in, and you have one of the hardest problems in mathematics. Andrei Kolmogorov, working in Moscow in 1941, found something that looked like a path through the obstruction. He could not solve the Navier-Stokes equations. Instead, he derived statistical laws about the energy spectrum of turbulence using dimensional analysis and a hypothesis about local isotropy, the assumption that at small enough scales, turbulence forgets the large-scale anisotropy of how it was forced, and becomes statistically the same in every direction. His result, known as the Kolmogorov -5/3 law, states that in the inertial subrange of turbulent flow, the energy spectrum E as a function of wave number, K follows E proportional to epsilon to the 2/3 times K to the power -5/3, where epsilon is the energy dissipation rate per unit mass. This was not derived from the Navier-Stokes equations. It was derived from assumptions about scale invariance. The law has been confirmed experimentally in wind tunnels, rivers, and the atmospheric boundary layer with remarkable consistency. It is one of the most reliably confirmed results in fluid dynamics. And it tells you nothing about why turbulence begins, how the transition works, or what the velocity field looks like at any specific point in a specific turbulent flow. It is a statistical average over an ensemble of possible turbulent flows. The flow in front of you is still unpredictable. This is where Feynman's specific frustration becomes clear. He had invented tools that made the previously intractable tractable, the path integral, the diagrammatic perturbation expansion, the renormalization procedure that absorbed the infinities of QED into measurable quantities. Those tools worked because QED has a small coupling constant. The fine structure constant alpha equals E squared divided by 4 pi epsilon naught times h bar times c, which evaluates to approximately 1 divided by 137. That number, 1 over 137, is the expansion parameter of QED. Because it is small, the perturbation series converges. The first term in the series gives you most of the answer. The second term gives you a correction smaller by a factor of alpha, roughly 0.007. The third term is smaller by alpha squared, roughly 0.000050. You can stop after a few terms and have extraordinary precision. The electron's anomalous magnetic moment, predicted by QED to 2.00231930.436 and measured at 2.00231930.482, agrees to 10 decimal places because the perturbation series is well behaved at coupling constant 1/137. The Navier-Stokes equations at high Reynolds number have no such small parameter. There is no coupling constant that lets you organize the calculation into a convergent series where the first term dominates. The full nonlinear behavior is present from the beginning of the calculation, at every scale simultaneously, and Feynman knew this was not an incidental difficulty, it was a structural one. He spent years trying to apply quantum field theory methods, renormalization group techniques, path integral methods, to the turbulence problem, and he did not crack it. He said so publicly, without qualification. Now step from the river into the nucleus. The problem changes, scale by 20 orders of magnitude, from meters to femtometers, from everyday fluids to the interior of a proton, but the mathematical obstruction is identical. The strong nuclear force is described by quantum chromodynamics, QCD, a theory formulated in its modern form by David Gross, Frank Wilczek, and Hugh David Pulitzer in 1973, for which they received the Nobel Prize in Physics in 2004. QCD describes the interaction between quarks mediated by particles called gluons, which carry a property called color charge, not color in the visible sense, but a quantum number that comes in 3 varieties conventionally labeled red, green, and blue. The force between quarks is carried by 8 different types of gluons, each carrying combinations of color and anticolor. The mathematics of this interaction is described by an SU-3 gauge theory, a non-abelian gauge field theory in which the force-carrying particles, the gluons, themselves carry charge and therefore interact with each other. This is the critical difference from electromagnetism, where photons carry no charge and do not self-interact. Gluons couple to gluons. The field equations are nonlinear from the start. The coupling is not weak. Gross, Wilczek, and Pulitzer discovered something extraordinary about QCD. At very short distances, or equivalently at very high energies, the coupling constant of the strong force becomes small. This is asymptotic freedom. The quarks inside a proton, when probed at high enough energy, behave as if they are almost free particles. The coupling constant alphas at the energy scale of the Z boson mass, 91 gigaelectron volts, is approximately 0.118. This is not as small as the fine structure constant of QED, but it is small enough that perturbation theory works at high energies. This is why deep inelastic scattering experiments at SLAC in 1968 and 1969, conducted by Jerome Friedman, Henry Kendall, and Richard Taylor, could see the internal structure of protons at all. At the high energies involved, the quarks scattered as if nearly free. Friedman, Kendall, and Taylor received the Nobel Prize in 1990. But at low energies, at the energies relevant to the proton structure, to the binding of quarks, to everything that makes nuclear matter what it is, the coupling constant is not small. As the energy scale decreases from 91 gigaelectron volts down toward 1 gigaelectron volt, alpha X grows from 0.118 to approximately 0.5. Below that scale, perturbation theory breaks down entirely. The series does not converge. Every term is important, and there are infinitely many terms. This is the regime of quark confinement. This is where the same disease that makes turbulence unsolvable makes QCD unsolvable. The equations are exact. The coupling is large. The calculation collapses. The confinement of quarks means that no isolated quark has ever been detected in any experiment. Every strongly interacting particle, every hadron, contains quarks in combinations whose total color charge is neutral, what physicists call color singlet states. If you try to separate a quark from its companions by injecting energy, as happens in a particle accelerator, the energy goes into stretching the color field between the quarks. The energy density of that color field, called the string tension, is approximately 1 giga-electron volt per femtometer, 1 billion electron volts per 1 quadrillionth of a meter. As you pull the quarks apart, the field stretches, storing energy. When the stored energy reaches roughly 140 mega-electron volts, for the lightest quark flavors, it becomes energetically favorable for the vacuum to produce a new quark-antiquark pair, which then screens the original quarks. You end up with two hadrons, not one hadron with an isolated quark. The quark cannot be pulled out. Every attempt to isolate it produces only more hadrons. This has been observed in every particle physics experiment ever conducted. Not once has an isolated quark been detected. The charge on a quark is 1/3 the charge of an electron, and no particle with fractional electric charge has been found in isolation. Confinement is one of the best confirmed phenomena in physics, and it has never been derived analytically from the equations that describe it. The tool physicists currently use to study QCD at low energies is lattice QCD, a numerical method developed by Kenneth Wilson at Cornell University in 1974. Wilson discretized spacetime onto a four-dimensional lattice with a spacing of approximately 0.1 femtometers and evaluated the path integral over all field configurations numerically using Monte Carlo methods. Lattice QCD has produced genuine results. The proton mass, 938.3 megaelectron volts, has been calculated from first principles to better than 2% precision. The masses of light hadrons have been reproduced. These are real achievements, earned by decades of computational effort and methodological refinement. They are also numerical approximations. Lattice QCD does not produce an analytic understanding of why confinement occurs. It confirms that confinement follows from the equations. It does not show the mechanism. Feynman's approach to QED was to find the physical picture behind the mathematics, the path integral as a way of summing over all possible electron histories, the Feynman diagrams as a way of organizing those sums into calculable pieces. He was explicit that he distrusted mathematics without physical pictures. He wrote in The Character of Physical Law in 1965 that he did not feel he understood a phenomenon until he could see the machinery, not just calculate the result, but visualize the process. QCD at low energies has resisted this. The color flux tube connecting confined quarks has been visualized in lattice QCD, narrow, cylindrical, approximately 1 femtometer in diameter, with constant energy density along its length. This is consistent with confinement. It is not an explanation of confinement. The flux tube is a consequence of the calculation. The mechanism that produces it from the gluon self-interactions, the first principles derivation Feynman would have demanded, does not exist. There is a candidate mechanism called the dual superconductor picture, proposed independently by Yoichiro Nambu, Gerardus Tuft, and Stanley Mandelstam in the mid-1970s. In an ordinary superconductor, pairs of electrons condense into a coherent quantum state that expels magnetic fields from the interior, concentrating flux into thin tubes. This is the Meissner effect, first explained by Fritz London and Heinz London in 1935, and given a microscopic derivation by John Bardeen, Leon Cooper, and John Robert Schrieffer in 1957. The dual superconductor picture proposes that the QCD vacuum behaves analogously, but with the roles of electricity and magnetism exchanged. Condensation of color magnetic monopoles would expel color electric field from the vacuum, concentrating it into flux tubes between quarks, exactly the geometry that lattice QCD shows. The picture is elegant. It connects confinement to a known physical mechanism. It is not proven. The color magnetic monopoles whose condensation would drive this behavior have not been rigorously identified in QCD. The picture is consistent with the data. It is not derived from the equations. The Clay Mathematics Institute's Millennium Prize for Yang-Mills theory and the mass gap formalizes part of this problem. The prize requires proving mathematically that Yang-Mills theory, the class of non-abelian gauge theories that includes QCD, exists as a rigorous quantum field theory and predicts a mass gap, a positive lower bound on the mass of the lightest particle in the theory. A proof of the mass gap would be a step toward a proof of confinement. As of today, no proof exists. The prize has not been awarded. The problem has been open for 25 years. Here is where the two problems, the river and the nucleus, converge on the same point, which is also the point where Feynman's legacy sits most uncomfortably. Both turbulence and quark confinement are problems of strong coupling. Both have exact equations, Navier-Stokes since 1845, QCD since 1973. Both have computational tools that give numerical answers without yielding physical understanding. Kolmogorov's scaling laws describe the statistics of turbulence without explaining its onset. Lattice QCD calculates hadron masses without explaining confinement. And in both cases, the difficulty is not a failure of the equation. The equation is the full story. The difficulty is that the full story written in mathematics cannot be read back out by any analytical technique currently known. The nonlinearity of the fluid equations and the large coupling constant of the strong force are at a structural level the same obstruction. In both cases, the perturbative expansion, The tool that works when the coupling is small diverges when the coupling is large. In both cases, the divergence is not a sign of wrong physics. It is a sign of wrong technique. This is a new kind of problem, and it matters to say so explicitly. For most of the history of physics, the unsolved problems were problems of missing equations. Newton did not know Maxwell's equations. Maxwell did not know Schrödinger's. Einstein spent the last 30 years of his life looking for a unified field theory that would require knowing something we still do not know. Those problems were problems of ignorance about the laws. Turbulence and confinement are different. The laws are known. The laws are confirmed to high precision. The problem is that the known laws in the strongly coupled regime cannot be solved. This is not a problem that a new experiment will resolve. No particle accelerator will discover a new force that explains confinement. No fluid dynamics measurement will reveal a hidden laminar structure underneath turbulence. The physics is in the equations. The equations are correct. The gap is mathematical. Feynman saw this clearly. In a 1983 BBC interview 5 years before his death, he said that turbulence was different from other unsolved problems, precisely because it was not a problem of not knowing what was happening. He knew what was happening. The Navier-Stokes equations described it exactly. The problem was that he could not extract the description into a form a human mind could follow. He had invented the most powerful analytical tools of his generation, and he knew their limits from the inside. The path integral works when the coupling is small. Perturbation theory works when the coupling is small. When the coupling is large, those tools fail, not by giving wrong answers, but by giving no answers. The series diverges. The calculation produces infinity. You know the equation is right, and you cannot use it. There are partial inroads. The ADS/CFT correspondence, conjectured by Juan Maldacena at Harvard University in 1997, relates a strongly coupled gauge theory in 4 space-time dimensions to a weakly coupled string theory in a 5-dimensional anti-de Sitter space. If this duality is exact, and it has not been proven to be exact, it would allow strongly coupled QCD calculations to be translated into weakly coupled string calculations, where perturbation theory works. It has been applied to the strongly coupled quark-gluon plasma produced in heavy ion collisions at the relativistic heavy ion collider at Brookhaven National Laboratory. The plasma's viscosity to entropy ratio, measured experimentally at approximately 0.08 times h-bar divided by Boltzmann's constant in units of 1/Kelvin, is close to the theoretical minimum predicted by ADS/CFT, h-bar divided by 4 pi times Boltzmann's constant. That agreement is striking. ADS/CFT is not proven to be exact for QCD, and the connection to full confinement physics remains out of reach. The turbulence problem has its own partial framework. Renormalization group methods applied to the Navier-Stokes equations, developed by Martin Forster, David Nelson, and Michael Stephen in 1977. These methods can reproduce Kolmogorov scaling exponents from a perturbative calculation, but only because near 2 spatial dimensions, the nonlinear coupling becomes small and perturbation theory can be applied. In 3 dimensions, the physical case, the coupling is not small and the calculation does not converge. The transition to turbulence, the mechanism of that transition, the precise Reynolds number, the structure of the instability, remains unpredictable from first principles for any realistic flow geometry. What remains after all of this is a statement Feynman would have accepted because it is exact and honest. We have 2 equations, Navier-Stokes and the Yang-Mills equations of QCD. They are correct. They have been confirmed in every experiment designed to test them. We cannot solve them in the regime where they matter most. Every proton in your body has a mass of 938.3 mega-electron volts, 99.9% of which comes not from the quark masses, but from the energy of the gluon field and the kinetic energy of the quarks confined within it. And we cannot derive that mass from the equations without a computer performing billions of numerical operations to approximate what the equations say. Every river, every cloud, every breath of wind is governed by equations we have had for nearly 2 centuries, and the detailed structure of the turbulence those equations predict cannot be obtained analytically for any realistic flow above a Reynolds number of a few thousand. The equations know the answer. We do not know how to read it. Feynman would not have called this a failure. He would have called it the next problem. But he would have been specific, and this specificity is the thing that separates Feynman's statement of a problem from everyone else's, about what kind of problem it is. Not a problem of unknown phenomena. Not a problem of missing equations. A problem of mathematical technique. The hardest kind, because there is no experiment that will solve it, no new measurement that will provide the key, no discovery of a new particle that will clarify the mechanism. The solution, when it comes, will come from a mathematician or a physicist, finding a genuinely new way to think about nonlinear equations, a new framework that can handle strong coupling the way Feynman's diagrams handled weak coupling. Feynman spent 40 years looking for that framework. He could not find it. The Clay Mathematics Institute has offered $1 million for a proof of the mass gap alone, not even full confinement, and has received no valid proof in 25 years. The problem is still open. The equation is still on the page. And the river, governed exactly by an equation we cannot solve, keeps flowing.